Today, we often hear rhetorics about peace and collaboration in the outer space. But to be honest, the reality is a little bit different. In fact, the space is moving very fast toward militarization, as the major space powers are decisively and swiftly developing their counter-space capabilities. When we say counter-space capability, the mind typically goes toward electronic warfare, jamming, or spoofing. But in fact, they are much more diverse. They are a range of capabilities with reversible or non-reversible effects. Let's take a closer look to some of those. The most benign case is a space situational awareness, or SSA, where the adversary using sets of sensors, for example, RF, radar, or optics, try to detect and characterize our satellites. It could be done on the space, we call it a space-based, or it could be done terrestrial. A classic case of the counter-space capability is electronic warfare, notably jamming, where the adversary could direct the jammer toward the satellites, we call it uplink jamming, or it could direct it toward a group of selected users, we call it downlink jamming. The adversary could directly hit the satellite using anti-satellite missiles, or ASAT. This is a Cold War technology. An interesting example of the counter-space capability is nuclear detonation. In fact, countries with a nuclear weapon can basically nuke their space. What will happen if we nuke their space? In fact, it will generate a huge electromagnetic pulse, or EMP, which is able to travel thousands of kilometers in the space. This EMP will induce a huge current into the electronics of the satellites and consequently fries the satellite. In fact, this is not a science fiction. This is very real. Countries such as ex-Soviet Union and the United States several times tested that in different orbits. For example, the United States, in a set of experiment called Fishbowl, tried to detonate nuclear weapons at different orbits. In an interesting case, which called Starfish Prime, they detonated a nuclear weapon 100 times more powerful than Hiroshima bomb. It generated a huge EMP, which immediately knocked out the streetlights in Hawaii, 1,400 kilometers away, and also it destroyed 6 LEO satellites. You should pay attention, at the time there were only a few LEO satellites on the orbit. Beside that, it also generated a beautiful aurora, which was visible from the Hawaii and Honolulu. You can see the picture on the right side. Though nuclear detonation in the space was nearly forgotten, at least in the media, until 5th February 2022, when Russia launched a satellite called Cosmos 2553. This satellite had a high level of radiations, and also it has a very unusual orbit. Its orbit designated to decommissioned satellites. Therefore, some experts believe that this satellite is carrying a nuclear dummy warhead. Regardless of if it is true or not, US DoD officials believe that in a foreseeable future, Russia will be able to launch at least one satellite with a nuclear warhead. Regardless of current geopolitical situation or environmental consideration, let's see what will happen if Russia today in 2025 detonate a nuclear weapon in LEO. According to the US officials, US DoD officials, quote, it will indiscriminately decimate all satellites within LEO, and also LEO space will be unusable for likely at least a year. Well, potential adversaries are not only focusing on developing their counter-space capabilities, but they're also developing their space capabilities. For example, China is very ambitious in low Earth orbit, or LEO. In fact, China planned to complete their mega constellation called a space sail with over 15,000 satellites by the end of 2030. And also they plan to have at least 3 mega constellations comparable to a Starlink by next decade with over 43,000 satellites. In this figure, you see the number of the LEO launches per year per country. As you can see, there is exponential growth for China and United States. Unfortunately, in Europe, we had a meaningful decrease in the number of our launches per year. Well, let's little bit narrow down our focus to the satellite communications or SATCOM. In 2025, today, the major vulnerability or concern in SATCOM is not nuclear detonation. In fact, nuclear detonation is highly unlikely. Instead, many reports and studies suggest that the key vulnerability of SATCOM today is unprotected waveform. You may ask me, what is a waveform? In fact, waveforms are sets of techniques to deliver IP packets. Here we are focusing on the lowest layers of the OZ model, which are physical layer, data link layer, and in some cases, network layer. In fact, US officials repeatedly warn about protection gap between commercial waveforms and protected waveforms. Protected waveforms in modern warfare are really problematic. For example, in the case of the Ukraine war, 1 hour before the invasion, Russian cyber attackers were successfully disrupted Viasat ground receivers. This put very critical ISPs out of the network for over 18 days. In the case of Starlink, Russians are persistently targeting and jamming Starlink with cyber attacks and jammer. The question is now what should be done or how we can mitigate? The answer is it is always the good practice to see what American has done so far regarding enhancing the protection of the SATCOM. And to do so, we should have a basic understanding of DoD SATCOM solutions. But as you can see, DoD SATCOM solutions are really complex and interconnected, as you can see in highly oversimplified figure. We have advanced extremely high frequency, MEOS, wideband global SATCOM system, and their interconnections. But the good news is they are simple to be categorized. US DoD SATCOM can be categorized into two major categories: MIL-SATCOM, which are the solutions owned and operated by DoD, and COM-SATCOM, which are the solutions leased by DoD. MIL-SATCOM could be categorized into three subcategories: narrowband, wideband, and protected. From each one, I will provide you a notable example. A notable example from the narrowband is Mobile User Objective System, or MEOS. MEOS consisted of 4 geosatellites. It adapted 3G technology, and it used UHF for service link, means the link between the user and satellites. And it can reach the rate up to 384 kilobps, which is good for transmitting voice and text. It works perfectly in adverse weather conditions and dense foliage. A remarkable example from wideband is Wideband Global SATCOM System, or WGS. It represents alone 70% of the worldwide military bandwidth capacity. It is huge. It's considered as a backbone of the US MIL-SATCOM. It is consisted of 11 geosatellites, and it can reach the rate between 2.1 gigabps to 3.6 gigabps. Well, during this presentation, you will hear the word protected, and you may ask me, what is protected? What we mean by protected waveform? In fact, protected waveform is a waveform that have some sort of some features, such as low probability of detection, low probability of interception, low probability of exploitation. It should be resilient against jamming. It should be resilient against cyber threats, cyber attacks, and so on and so on. A good example of the protected SATCOM solution in US DoD solutions, among US DoD solutions, is Advanced Extremely High Frequency, or AEHF. AEHF could be served for strategic and tactical missions. It used 3 types of waveform: low data rate, or LDR, medium data rate, or MDR, and extended data rate, or XDR. It consisted of 6 GEO satellites, And for the uplink, it used the band at 44 gigahertz. And for downlink, it used 20 gigahertz. So its uplink is actually located at extreme high frequency. That's why they called it advanced extreme high frequency. As you may already notice, only a small portion of the US DoD SATCOM solutions are protected. The question is, why so? The answer is simple. In fact, for decades, United States enjoyed of being unchallenged in the space. No other competitor. So therefore, most of the design are based on no threats in mind. In fact, the system designed based on long-term functionality, efficiency, and cost. The old vision is no longer valid. According to the new US Space Force satellite vision, which is published on 2020, in order to enhance the SATCOM protection, there should follow two strategies. The first one is disaggregation strategy, where they're separating tactical and strategic SATCOM solutions from each other. This should be completed in 2030. The second strategy is following a family of programs called Protected Anti-Jam Tactical Programs, or PATS. These programs dedicated to enhancing wideband and ComSatCom protections. This should also be completed in 2030. Accordingly, by 2030, the missions of the advanced extremely high frequency will be transferred to two separate SATCOM solutions, which are Evolved Strategic SATCOM, or ESS, and Protected Tactical SATCOM, or PTS. ESS will take care of the strategic missions, and PTS will take care of the tactical missions. Protected Anti-Jam Tactical SATCOM, or PATS family of programs consisted of two major program lines. PTS, or Protected Tactical SATCOM, which take care of the development of the space segment, and Protected Tactical Enterprise Services, PTES, which should take care of the development of the ground segment. Both program lines centers around a waveform called Protected Tactical Waveform. In fact, PATS has three major program lines, three major phases. During phase 1, PTW should be transmitted over WGS. Here, WGS plays the role of the band pipe. In phase 2, PTW should be transmitted over commercial satellites. And in phase 3, PTW should be transmitted over regenerative, fully regenerative PTS payload. In fact, PTW, or Protected Tactical Waveform, will play the key role in the future of the tactical DoD SATCOM. PTW is based on very classic waveform called DVB-S2, or Digital Video Broadcasting Satellite Second Generation. This waveform existed since 2005. It's used in many modern satellite TV channels. Many TV channels that we are watching from the satellites are based on this waveform. This waveform enjoys of two layers of the forward error corrections, which are LDPC, or low density parity check, and BCH. To mitigate burst error, it used a mechanism called interleaving. Well, they add two extra security features to this waveform and build so-called PTW. These security features are time diversity and frequency diversity. Well, frequency diversity is simply frequency hopping. You can see those added features in the green boxes in the right figure. You may ask me why, for such an important waveform such as PTW, they use such a known and classic waveform. It means DVB-S2. The answer is affordability and interoperability. In fact, they wanted to reuse actually the terminals, the commercial terminals, with the minimum of the upgrades to be able to use PTW. That's why it is good for the commercial sectors because they needed only the minimum level of update to their terminals. They don't need to design everything from the scratch. Well, in the era of the broadband SATCOM, there is a new game changers, which are mega constellations. We all witnessed the tremendous success of the Starlink against Russian jammers. We often been asked why our mega constellations are resilient to jamming. The answer is two-part. First, compared to the GEO satellites, mega constellations are located in LEO. Therefore, they are 10 to 100 times closer to the terminal. Therefore, they are offering much stronger RF signals. Also, if the jammer successfully managed to jam one satellite, the victim can easily switch between the satellites and switch to another satellite because it is using software-defined radio. Therefore, it is very agile. It can switch very simple to another satellite. Therefore, just as an example, in the case of Starlink, at any given geographical point at any given time, there are between 8 to 49 LEO satellites visible. Each satellite has 6 to 8 beam spots. Therefore, if the adversary needs to jam or block the whole service, it should jam between 48 to 294 RF bands. Good luck. Most of the mega constellations that we know, such as Starlink or Cooper or OneWeb, they are based on the commercial waveforms, means they are not based on open standard. In recent years, 3GPP, which is a standardization body or third generation project partnership, made a huge step toward this space by introducing open standard for broadband SATCOM. Actually, they have done it for the feature called integration. They wanted a space, airborne, and terrestrial networks seamlessly work together. The standard came in different releases. For example, release 8.17 is based on transparent architecture. Release 18 is based on regenerative architecture, where they actually move the G-node B, or simply loosely speaking, the base, to the satellite, the base station to the satellite. Well, now let's fly together over the Atlantic Ocean and come to Europe. What is going on in Europe? In Europe, we are designing a waveform called European Protected Waveform, or EPW. EPW is a 12-nation effort to develop the first European protected waveform for SATCOM. As you may see here in our consortium, you can see the big names such as Airbus, Eutelsat, Thales, Lasting Software, and the companies are led by a Belgian company, ST Engineering. Regarding the current geopolitical situation, it is needless to say how it is important for EU autonomy to have a secure and independent SATCOM solutions that could support wide range of the military operations with different requirements. EPW is based on the new space concept. It means it should support multi-orbit, GEO, MEO, and LEO with a focus on Iris Square. Loosely speaking, Iris Square is the equivalent of the European Starlink. It should support regenerative and transparent satellite architectures. As the name suggests, it should be protected, means resilient against jamming, resilience against cyber attacks, LPD, LPI, LPE. And also, it should incorporate advanced SATCOM technologies such as DVB-S2 and 5GNR. EPW is a multi-year project. Currently, we are in phase 1, which is a study and design. It is an EDF project with over 30 million euro of funding. The phase 1 consisted of 2 parts, a study where we gather all requirements for the system, I don't know, terminals, ground terminals, or spaceborne elements, and so on. And in the design part, we actually designed the waveform, and even simulators and ground stations, terminals, a spaceborne payload, and so on. So it is not only a waveform, it is a protected waveform system. It is a system, and all requirements and design will be published in a book, in a blue book of the EPW. At the end of phase 1, there will be also an over-the-air test or demonstration. As you can see, EPW consisted of 15 work packages that cover the early use case definition, requirement gathering, and even the spaceborne design and ground station design, and so on. Currently, we are near to the end of the project. We are so close to the end. Conclusion. By the end of 2030, well, it is not a good idea to do predictions, but let's see at least what should be expected by the end of the 2030. By the end of 2030, the US disaggregation strategy will be completed. US PATS family of programs will be completed. US evolved strategic SATCOM will be operational. US protected tactical SATCOM, which is using PTW, will be operational. China space sales with over 15,000 LEO satellites will be completed. And hopefully, IRIS², at least the governmental service, will be operational. Thank you very much for your time and attention.